All right. What do you think? You guys ready? So
Yeah.
I'll give you
Yeah.
just a quick introduction, and then you can take it away. So, welcome everyone. Thank you for joining us today for this honors talk. This term, Shantanu Tavkar and Madison Manjarrez worked with me studying cryptography. They've done a phenomenal job, and they focused on. They did a lot of things, but for this talk, they focused on looking at problems associated to this discrete log problem, Diffie-Hellman key exchange, some really interesting number theory and mathematics that is behind how all of our electronics, our web browsers stay secure. And then along the way, they also programmed everything in Python and Sage, and I think they're going to be showing you some of that as well. So it's really they did a really impressive combination of theoretical mathematics and implementation with programming. And with that, Madison, Shantanu, please take it away.
All right. Yeah. Thank you, Jeff. As Jeff mentioned, we're going to be focusing on the discrete log problem and how that helps us in cryptography. So let's get started.
All right, so we want to start with kind of the big idea of what cryptography is. So in today's world, we're always communicating online, whether it be this Zoom meeting, any web browsers, and we want to make sure that these are all kept private and secure because a lot of sensitive and personal information is being shared. So luckily, these platforms that we're exchanging information on, they use cryptography as a way to ensure that we maintain this privacy. And so we'll be talking about how a crypto system like this can function and how we can exchange information and ways to ensure that we have the maximum amount of privacy as possible. So we'll be using public keys to make sure that this is possible. So a way to kind of more simply explain the bigger picture is through the problem that's facing Alice, Bob, and Eve. So Alice and Bob are just two parties. They want to communicate with each other, but they want to do so privately so that an outsider, Eve, can't listen into their conversations. So their goal is to create some way to exchange messages, and we want them to be able to exchange messages very easily with each other, but we want to make it difficult for Eve if she's trying to eavesdrop in on their conversations. We want it to be a problem for her to get in the middle and find out the information or change the message or any sort of deal. Go ahead, Johnson.
So a way to look at this is the lockbox metaphor. So in this metaphor, everyone has a public box that is available to anyone to fill with information. And anyone wishing to send a message can put that message in the intended receiver's public box and then lock it with their public key. And then once it's locked, only the owner of that box can open it with their personal private key when locked. So we want to show an early version of kind of ciphering messages and locking them. And this would be the Caesar cipher. So it's fairly simple. Basically, it encrypts messages by shifting the alphabet by an agreed amount. And then to decrypt, you would easily just decrypt it by reversing that shift. The hard part is just knowing that shift. And then this shifted amount would be kept secret from everyone else outside of the communication line, such as Eve. So we coded a version of this. And we added two conventions. The first one being we want to turn the message into all capital letters. And then we want to insert a space between every 5 letters. And these are added just to prevent any patterns because you could easily kind of figure out some simple words like the or a if they keep repeating over and over. So here's our Caesar cipher function built on Sage, and it basically takes in a message as a string. So when you see a quotation, that'll mean it's a string variable. And then the integer amount, the shift. So basically, you'll see it turn first the message into all caps, and then it'll start shifting it. And then finally, it'll start adding the space between every 5 letters. And then once that's all done, we put it all back into one encrypted message. So our first example is just a proof of concept. So let's say we would just want to send ABC shifted by 1. This is how it would show up. Let's say B was not capitalized. We still want things to be all caps. And then this is something a little more of what might get sent. So let's say we wanted to send this message and then shift the alphabet for each character by 14. We would enter that message in the shift, and then here's what we would get. So someone on the outside seeing this is going to have a pretty hard time finding patterns and understanding, what is being said here. And kind of a way to see what's how it's working is we can reset it by shifting back to the original. So if we run this, you can see the original message back, but this is not how it would be decrypted, but just a kind of a visualization for what's happening here. So yeah, that's an early version of the encryption with the Caesar cipher.
And although the Caesar cipher, it served its purpose a long time ago before we had computers that can make a much better cipher, there were some issues with it that are, by modern standards, there's some issues with it. So first of all, this requires the 2 parties to meet in person to agree on a shift value, and probably meet in person often to keep updating their shift value to ensure that they're the most private as possible. And also, as you can imagine, with today's computers, this would be not too hard for someone in the middle to figure out, because it's a very simple cipher. So I guess now that brings into what do we want for what is our goal for modern cryptography? So we want a way that, again, to reinforce, we want Alice and Bob to be able to send and receive messages that is easy and fast. But we want, if Eve is trying to eavesdrop and get in the middle of this conversation, find out what the messages are, it's going to be very difficult and slow for her. And so that's exactly what the discrete log problem purpose is. So basically this discrete log problem is an example of how it can be difficult to reverse a quick process. So we can exponentiate mod n quickly. This is a quick calculation. And for those of you who don't know what mod n is, that just means basically divide by n and then keep just talking about the remainder when you divide by n. And so we can exponentiate really quickly, take the remainder, and that's a very quick calculation to perform. However, if we try to reverse this calculation logarithmically, this can take an extreme amount of time, especially if we cleverly choose the components of our exponentiation. And so now we have a problem it's easy in the forward direction, so it's going to be easy for Alice and Bob to do. But if Eve is trying to reverse this calculation and she's trying to find our exponent, she's going to have a really hard time. She's going to run into the discrete log problem. And so we can use this to our advantage when we're sharing information. So I'm going to go ahead and share my screen and kind of show you guys a visual for what the discrete exponential function looks like. Sorry, give me 1 second.
Should be useful, I think.
Yeah, just the Zoom camera.
Oh, yeah.
Okay, so if we can compare a range of x's and compute y. So we're going to just exponentiate mod p. So we're going to look at g to the x mod p. And here's what that function would look like. So I chose the p to be 97 and the g to be 3. So as you can see, this function is definitely not continuous, which is great because that means that there's not much you can't really predict where the next outcome will be. Because a continuous function, if we have a small change in input, there's going to be a small change in output. But this discontinuity is going to help us out. So, so this is pretty good. We can see that this is definitely more randomized than if we were to use a continuous function. But if you guys can notice, there's sort of like, it's like a patterns repeating. And that's actually because we're not using a generator of the multiplicative group mod P. So let me kind of show, and then I'll further explain what that will look like. So we could see this does a better job of randomizing what the discrete exponential function looks like, and therefore it would be harder to predict where values would be. So here we would have what would be available to the world to see. So this would be public, your y values, but it would be very difficult to find the x value that corresponds. So that's the problem that Eve is going to run into. So we can kind of take this a step further and even show more disorder if we make our p value even larger. So we can look at with 1009 and also using a generator as your g value. So when we use a generator, those of you who have taken group theory will know that the generator is able to produce the whole group. So that's why we don't see the repeated pattern. And so you could see this is an even better improvement to the smaller prime p. And if I go back to using something that's not a generator like 7, there's more predictability in patterns being shown. So, so this is exactly what we want to use. We want something, a discrete exponential function that looks something like this. And relatively speaking, 1009 is actually a very small prime. We're going to be using much, much larger primes to ensure that this is even more secure.
All right, so before we get started on kind of the bigger picture, we want to talk about some of the smaller, more useful algorithms that we use to help us get there. And then the first one is fast powering. So like Maddie mentioned, we want to use, we want it to be as scattered as possible, and that part of that involves exponentiating large x's. And so we want to quickly do this using the binary form of x, and we'll show you how that works. And then another useful algorithm is the extended Euclidean algorithm. And this one's really important because it finds the coefficients of S and T such that S, A, and TB are equal to the GCD of A, B. And it's significant because when A and B are relatively prime, that S represents the inverse of A mod B. And Maddie will talk about that. But first, let me show our fast powering. So in order to fast powering to quickly calculate g to the n mod m for large n, first we need to turn n into its binary form. So this function does that. If any of you have calculated binary before, basically it involves recording the remainder all the way down until you get to quotient 0. And then you basically reverse the list and you will have produced its binary form. So let's say, for example, for n, we wanted to use 2301. Its binary form would be returned like this. And basically, what this represents is the powers of 2 that are visible in Rn. So starting from right to left for binary, you're going to have 2 to the 0, 2 to the 1, 2 squared, 2 cubed. So this is important, as you'll see in fast powering, because fast powering will look for those ones to show, to let us know which powers of 2 are present, and only power those aspects of n to help make this powering go much quicker. So let's make sure these are run. So here's an initial example. Our G is going to be 3. It's going to be powered to 23 and then mod M of 127. So we're going to compare compute times using just a regular G to the n mod M, just telling our program to compute that. And then we're going to look at fast powering. So this initial example, you can see fast powering is slower. It's a great example of how sometimes your algorithms, depending on what calculations you're making, sometimes a simple one is the best way to go. But let's see what happens as we gradually increase n. Run that again. So yeah, as we can see, it's still faster. Both are still under a second, which is good. Let's increase it just a bit. So you can see now it's a little faster, but again, both are under a second, and depending on what you need to do, this may not be worth the difficulty in coding. And then our final n, let's take a look. So when you see this asterisk here, that means it's still computing. So you can see now, I mean, I have this much time to talk while it's still computing. And in modern computing, this is a very long time to wait for something seemingly simple as exponentiation. So it should be solved fairly soon. Around 37. There it is. So this took 43 seconds. And let's compare with fast powering of the same values. Done. This is where fast powering shows its usefulness. For large, and it really helps to, one of the main things we kind of learned was breaking down large problems into smaller, more workable, and breaking down n into a much easier and workable number can really cut down our computation time. So then let's move on to extended Euclidean with Maddie.
All right, many of you guys might be familiar with the extended Euclidean algorithm if you guys took number theory, but Shantanu, you could scroll down and show an example. We'll look at it through an example.
Sure.
So as Shantanu kind of mentioned before, the extended Euclidean algorithm is going to find coefficients S and T that make it so that the GCD of A and B is SA plus TB. And so you could see from this example, if you look, we're going to use the regular Euclidean algorithm, which is used to find the GCD of two numbers, A and B. And so we run through this process of finding quotients and remainders until we finally get a remainder of 0. Once we get a remainder of 0, we know that the previous step's remainder is our GCD. And now we can use this, just that itself was the Euclidean algorithm, and we could use this, solve for R, and then sort of do a replace and organize system where we end up with our coefficients of S and T. And so here we have 6 would be our S, and negative 23 would be our T. So we see that the GCD, so the GCD of 126 is going to be 2. And so the unique coefficients are going to be 6 and negative 23. So that's what we have our function returning right there. So this is interesting, but for our purposes, this algorithm is actually even more interesting and useful to us when we're working with A and B that are relatively prime to each other. So in our next example, we use 92 and 35, which are relatively prime numbers. And so that just means that their GCD, their greatest common divisor, is 1. And so again, we're going to run through a similar process. And in the end, we find out their coefficients are 8 and negative 21. And so this is extremely useful to us because this actually says that 8 is the inverse of 92 mod 35. So to explain this, we can actually look at that last line. 1 equals 8 times 92 plus negative 1 times 35. And so we're going to be working mod 35. So when we're working mod 35, this negative 21 times 35, if we take that mod 35, we're going to get 0 because 35 is a factor itself. And so that part's going to go away. So now we have that 1 equals 8 times 92 mod 35. And so what that tells us, since we're working in a multiplicative group, our identity element is going to be 1, because anytime, if we take any element in the group and we multiply it by 1, we're just going to be returned what we started with. So we have 8 times 92 equals 1. So anytime we have two things that give the identity, we know that those are inverses. So again, to repeat the main idea here is that now we find out that if we're given the EEA of A and B, then we can use the extended Euclidean algorithm to find that S is actually the inverse of A mod B. And so we're going to be using this result a couple times, and its main purpose is going to be to find inverses. So I thought this was a pretty cool use of this algorithm that I learned before, and kind of applying it to group theory, and it's going to be actually really useful to us in our functions we're going to show you later.
All right, and then we have a couple more useful algorithms. And those two are standard encoding and standard decoding. So standard encoding works by converting, taking a string M and then converting each character of that string into, or converting the whole string M into a unique integer using Unicode standards. Basically what Unicode is how your computer is reading every character you type in. So each character is going to have its own unique Unicode integer, and that's what our standard encoding uses to create our full integer for string M. And then standard decoding will take an integer, en, and it'll just undo the whole process of standard encoding to get back to a message string. So we want to show that. So it's a fairly easy function. It uses ORD of A, and ORD returns, given a character, it will return an integer value. And that's important to us here for standard encoding. We can show that by showing a message, a string that just says hello. And then you can see each character of this string, and not just for this string, but in general, every time capital H will be equivalent to 72, E is 101, and so on. So taking these values, standard encoding will create one large integer. And you can see each component of that string is still visible. So 72, 101, the two 108s for our two Ls, and then the three ones for our O. And then standard decoding is going to take just that whole process and reverse it. So we're going to divide by 1,000 to break apart each letter. And then we're going to now use char, which now takes integer R and then gives us a string or a character to work with. So reversing that whole process, we put it back into a string. And now we have our message again. So let's say I wanted to send a message, thanks for coming today, everyone. We're going to take that, put it into standard encoding. And this is the integer we're going to get back from it, if you recognize the hello there. And then let's say someone getting that message, they were sent en. They're going to take en, put it in standard decoding, and they're going to get that string back. So this is useful for encryption because now we have a number, an integer we can work with and manipulate that represents a string. So yeah, these are super useful to encrypt. Then we'll move on.
So now we're going to talk about Diffie-Hellman key exchange. So in this key exchange, we're going to be using the public parameters that I talked about earlier. So the large prime P and the generator G. And these public parameters will be decided by like a trusted third party. And so Alice and Bob are going to use these public parameters and to be able to create public keys. But first they're going to create private keys, little a and little b. And they're going to keep these completely private from everyone. They're only going to have them for themselves. They don't want anyone to find out their private key. And then they're going to use these private keys to compute public keys. So they're going to do this by using the public parameters that were established, so P and G, and as well as their private key. So what Alice is going to do to compute her public key is she's going to do G to the A mod P, of course using our fast powering algorithm so that it's a much faster process. And so she's going to come out with A, which this capital A is what she's going to give out to the world. She's going to publish this capital A. This is her public key that people can use to share information with her. And Bob is going to do the same thing using obviously his private key to make that computation. And so this is going to allow them, now that they have their private and their public keys, they're going to be able to create this shared secret number. So for Bob, what he's going to do, since capital A and capital B are their public keys, these are out there for the world, they're published. So Bob can easily find Alice's public key, and he can raise this to his private key. So you could see that would be capital A to lowercase b. And Alice can take Bob's public key and raise it to her private key. And so you could see by just rules of exponents that these turn out to be the same number. So now we have a way where Alice and Bob can share some information out to the world, keep their private keys private, but still be able to have a common ground, which is this shared secret number that they can then use later on. And now Shantanu is going to talk about a way that this can be used in message exchange.
So building off that secret number, now we can combine everything we talked about to securely exchange messages. So fast powering again, like Maddie said, to create the public keys. EEA will come in handy when we want to take that secret number and find the inverse of it. And then of course, standard and encoding and decoding help us manipulate integers that represent strings. And then the Diffie-Hellman key exchange gives us the use of the secret number, which we will be using to encrypt and then decrypt messages. So let's go on. So you can see all of our functions are now being used to send messages. So here are the here's the prime and the generator, and these are going to be public, available to everyone. These are going to be agreed upon. The secret's out. Here's my private key, and this is what I'm going to be using throughout LGAML. And then using fast powering, this is my public key. And like Maddie said, I'm free to publish this anywhere. I want people to know this so that they can communicate with me. And I have Madison saved here because we're going to be communicating. So LGAML can be split up into two parts. Basically, if you're going to be sending or if you're going to be receiving. If you're going to be sending, you want to have a message ready and the receiver's public key. First, you want to create an integer you can manipulate. So you're going to standard encode your message. And then you're going to create C1, which is basically the computation of your public key again. And then you're also going to calculate C2, which involves the use of our secret number. So if you can remember Maddie talking about the sender taking the receiver's public key and then raising it to their own private key. Here you see that secret number in action. and it's being multiplied to our encoded message to encrypt it. This is the actual encryption process. Once we've calculated our C1, C2, we're going to return these. Now let's say you're a receiver and you've received a C1, C2. You're going to input them into your function. And first, you're going to, again, calculate your shared secret number. So again, you're going to take the public key of the sender this time, and then you're going to raise it to your own private key. And here's where we need extended Euclidean, because it helps us find the standard inverse between two relatively prime numbers. So once we do that, we're going to multiply the inverse to the message, the encrypted message we received. So this part will be undoing what our sender did. So using the inverse of our secret key, we're going to uncipher it. And then now we have our just bare integer that just needs to be decoded. So once we've unciphered it, now we can decode it. And then finally, we've created our, or we've decoded our integer into a string. So let's say this is, I want to send Madison my deepest, darkest secret. No one can know about this. All I need to say, or all I need to give sender is my message and then who I'm sending it to. Let's make sure that's running correctly. There we go. So here we have sender, and all I'm sending her is my C1. You see this large number here, and then my C2. So I can share that in chat. And this is what kind of, this is what Eve would be seeing. And then Madison, you can take over.
Mm-hmm. All right, so I'm just going to be using exactly what Shantanu sent me into our receiver function. And so this is exactly what he sent me. He sent me his public key and then the C2 that he computed. And so I can use my receiver function. Oh, sorry.
Oh, just compile.
Yeah. And as you can see, I was able to find out his deepest, darkest secret. All right, and then going back.
Sorry, just a sec. Mm-hmm. Okay, so signatures. So now with LGAMO, we've ensured eavesdroppers cannot decipher your messages, but that's not enough. Eavesdroppers can still get in the middle of your exchange and then manipulate the messages, which could lead to a scenario where Bob and Alice are talking, never realizing that someone is manipulating their messages and they've never heard the intended message from each other. So now we want to talk about signatures because they allow us to verify not only the identities, but also the content of their messages. So that leads us into DSA.
All right, so DSA is a signature algorithm that allows us to authenticate the sender, which means that we're ensuring that who we think we're talking to is actually who we are talking to. And then it also is going to verify the message. So it's going to verify that the message that the sender wanted to send is actually the one that you are receiving. So again, the digital signature algorithm is going to use the discrete log problem to keep these signatures safe from forgery. And it's also going to utilize secure hash algorithm 256 or SHA-256, which will serve as sort of like a check digit, which I'll get into more a little later. And so basically in this DSA exchange, what's going to happen is that Bob is going to create a unique signature for his message. So he's going to compute R and S and send that to Alice. He's going to use his private key for this. And then Alice, once she decrypts the message, she will then look at his signature and be able to authenticate the message and make sure that it's actually Bob that is sending it. So let me move over to our functions. So as I mentioned before, we're going to use SHA-256 in this algorithm. So we have a function here, standard hash, which uses SHA-256. And as I mentioned before, it's sort of like a check digit. So it's something that takes a string, a message, and it's going to jumble it up and produce some integer. And so this integer, it looks very random, but it's very deliberate, and it's very unique to the specific message we send. So you can see this if I hash this message, hash browns for breakfast, we could see the integer that's produced by this. And if I, even in the slightest bit, alter the message, so this time I just changed the uppercase H to a lowercase h, and as you can see, this produces a completely unique integer from, it's completely distinguishable from the very similar message. So this is going to be used in our digital signature algorithm. So for this algorithm, there's going to be a couple more parameters. It's going to be Q, P, H, and G for this algorithm to work. So as I mentioned before, the sender of the message, they're going to produce a signature that's specific to this message. And they're going to use this hash function, and they're also going to be using, they're going to be producing R and S, which are the components of the signature. So the sender is going to send the signature, and then the authenticator, so the receiver, is going to also use hash, and it's going to use the sender's public key and produce A, which A, if everything went well and the message is true to what it was and it's from the right sender, then A in the end should come out to be the R that was sent as part of the signature. And so if this is all working correctly, we should get a true for authentication of signature. So I can show you guys how this will work. I'll send a signature for Shantanu to verify. So what I'm sending him is my message, I'm sending my public key, and then I'm sending my components of my signature, which are the R and S. So I'll send this in the chat, and you guys can see how it looks in there. And then Shantanu is going to use this to then authenticate the message I'm sending.
So let's take what Madison sent me, paste it, get rid of ugly Zoom chat formatting, and then let's verify that it's actually from Maddie. And you can see it's true. And a quick, a simple demonstration of this is if Eve happened to change any part of this message, we should see this should point out any sort of manipulation, which it does. So if Eve now is in the middle trying to alter or change messages, the signature is gonna catch that something, whatever Bob wanted to send to Alice has been changed, and it's not what Bob meant to send to her. So it's a great way of catching that. So then once we've done our DSA, now we combine everything. Now we want to take LGAML and we want to add DSA to it. So once we've combined these two, the sender now can generate an encrypted message with a unique signature. And the receiver can take this and now decrypt the message and authenticate not only the person sending it, but also the content of their messages. So here is kind of the final LGAML, everything combined together. You can see you can look at them as separate processes, but still the sender, all it needs is the original message, M, and who it's going to. And LGAML will still continue to produce C1, C2. It's still using the secret number. And then DSA will create a unique signature every time for the message by creating a random K, which is used by R to power, to exponentiate, and then use as part of the signature. So the DSA will again hash the original message to create that unique integer, and then it will create R and S as part of the sender's signature, and it will return all of these aspects to the sender. So the C1, C2 from Algamel, the signature, and then their own public key to be used later. And then the receiver will take all of this information, same things, the public key from the sender, and it will reverse the process. So again, what you've seen in Algamel, create the secret number, find the inverse of that secret number, uncipher it using that secret number, and then finally decode it. Here, what we do, as Maddie mentioned, standard hash is the check digit. You can think of it kind of like that from ISBN numbers, which basically means we're going to take our decoded message and we're going to try to recreate the signature that was created up here. So we're going to standard hash that decoded message, and then we're going to calculate A. And then again, we want to print the received message, and then we want to check, hey, was our recreation the same as what was sent to us? If it is, then we would have verified that we did in fact get it from the intended receiver and that this is what they wanted to send us. So let's see it in action. Let's say this is the message I want to send and I want to sign it. I want to say, hey, it's from me. Again, all I give it is the message and who I want to send it to. Let me run it again. There we go. And you can see, yeah, a lot more outputs because we need a lot more done. And then let me send this again in the chat. Go.
All right, and then I'll use this information that Shantanu sent to me, and I'll try to receive the message. Let me just fix some formatting, and then I'll be able to show you guys. All right, so this is all the information that was sent to me. So now I'm going to verify that this is in fact the message that was intended for me and that the sender is who I think it is. So here we see I successfully received the message from Shantanu, and then I can also feel secure and that this was what was meant to be sent to me and from who I am thinking I'm talking to by using our DSA algorithm to authenticate the signature. And so I can, let me just do a quick example. So I'll use the sender function just to say hello. And so I just wanted to point out that each time that we are sending something, because we are using, we're creating a unique signature each time. So even if I send a message in 2 separate instances, it's going to create a unique one every time. So so here's what I produced now, but if we pay attention to the signature, it'll even change if I run the same message again. So it's constantly updating and making sure that we aren't, we're as secure as possible using these random integers.
So just to kind of recap, there are robust encryption methods in place to help keep information secure for us, for companies, for government organizations. it can be a little easy to kind of assume privacy when there's only two parties present in a communication line. But it's great to know that there are encryption methods in place, and key exchange algorithms that utilize the discrete log problem ensure malicious third parties, like Eve, can't easily intercept important information. And using the irreversible property of exponentiating with large prime values, eavesdroppers will be, long dead before they can solve any individual key. It would just take forever. And then while we're on the subject of encryption, just a timely subject, let me just take the screen over real quick. Something to consider. You might have heard of it, the Earn It Act. And one important part of it is it wants to tackle end-to-end encryption. It wants to take it away. And this is something everyone should care about, as it has to do directly with your privacy. So, me and Maddie have shown just how easy it is to create encryption, and leaving a backdoor for law enforcement or the government also means now there's a backdoor for hackers, and kind of trying to stop them, or it's going to be a little hard to stop them because they already know how to encrypt. And like, again, me and Maddie just proved we can do a simple encryption within 10 weeks. So this is something to think about. Encryption is important. So educate yourselves if you can, if you already haven't, and just something to leave you guys with. Anything else to add, Maddie?
Yeah, I think if anyone has any questions, now could be the time to start answering them.
While people are thinking about their questions, I want to say how impressed I was with those handoffs throughout the talk. I don't know if you in the audience can appreciate that is a non-trivial task, and that was seamless. So that was really impressive.
Thank you. Thank you.
Mm-hmm. We had a whole playbook.
Yeah, but are there any questions in the audience? Oh, there's a question. Will these recorded math talks be available? Yeah, so we're putting these talks on the events page on the CSU math website. So you'll be able to see all of the talks this term from speakers who've given their permission to have their talks recorded and posted. But there are questions for Madison or Shantanu? Oh, yes. You guys see that, or I can?
Oh yeah. So we used Sage Math. Which is built off Python. So it's just kind of math libraries that are added onto Python. But a lot of this you can just say was in Python. And Python is really popular as a math language. You can see it used a lot in data science and statistics. So it just made sense. And it's also really approachable and pretty easy to take on. Everyone should dabble a little in Python.
Other questions? All right. Well, I think there are no other questions. So let me just say the two of you did a fantastic job this whole term, but also in this talk. It was very impressive. So I thank you for your hard work. Well done, and everyone here. Let's thank them for giving this fantastic talk. Well done.
And yeah, we want to thank you, Jeff, too. This is a great just experience. I learned a lot. If anyone's interested in doing an independent study with Dr. Meyer, it's something to consider.
Yeah, thank you, Jeff. And just to everyone, if this interests you, if you want to know a little bit more about cryptography, Sergio is going to be giving a talk in an hour, right?
Yeah,
so if you guys want to know more, come to that too. He'll be talking about some interesting stuff.
This was fun. Thanks, guys.
Thank you, Brenda.
Thanks for coming. All right.
For the talk, guys.
Sean.
Thanks, Jay. All right.